Good morning, Baby Friday. I am so happy to make it to yet another Baby Friday. Welcome to the OscopeWizard show. I'm the OscopeWizard, I'm Gabe, and you have landed on a delightful nerdy sequence that will last about half an hour, where we are going to explore electronics and other nerd topics that tickle my fancy. Hopefully, you are having a wonderful, spectacular, awesome Baby Friday as well. I have decided that Baby Friday is my new favorite day of the week. It used to be actual Friday, but you know what? If we just move the week's soft close up one day, that makes the week so much shorter and so much better and more awesome. And that's where we're at. That's where we're at. We're at an awesome Baby Friday. And we are going to spend the next few minutes discussing the next step of our DIY Sonos style amplifier. In the last few episodes, we've outlined and reviewed different operating systems that we could choose to put on our Raspberry Pi, which is the brains of the operation of our Sonos style amplifier. And we chose, after much deliberation and consternation, to try Moode audio. That's M-O-O-D audio. That's the operating system that we chose to install. We tried Volumio. We tried Max to play. We settled on Moode. It fit all of the goals, or it nailed all of the goals. The goals were the amplifier has to support AirPlay. The amplifier has to have a Bluetooth speaker function, and the amplifier has to have Spotify integration. Moode audio did all of that for the wonderful price of $0, which is a good price. That's a good price for the software. Now we're going to probably have to expand this software a little bit, but that's going to be on my own with my little fingertips programming in some kind of language, most likely Python. That's down the road. Now the next step in our odyssey is to add some volume control to the front of our amplifier, some kind of a knob that can be turned, because what kind of amplifier is it without a knob? You gotta have a knob, you gotta have a button, probably a light. There were some requests, in fact, to add the Rotary Encoder function to Moode, because I noticed in the settings of Moode audio was an option to add a Rotary Encoder, and that is where we find ourselves today. Why would I choose a Rotary Encoder over a potentiometer? A potentiometer is the traditional method of controlling volume. And what's the difference between a potentiometer? I can't even speak. What's the difference between a potentiometer and a rotary encoder? So we're going to get to it. We're going to explore. We have our timer here. We're going to start our timer so that we stay on track and we don't lose all track of time and space. And we'll begin. I have in front of me on the desk, I have a potentiometer. Right here, you can see it. Let's see if I can get my camera to focus on it. It is, well, did we find it? Didn't find it. Find it. There we go. That's it. It's a knob. It's a knob. One of the things that potentiometers can do are turn, but they have limits. So that is one extreme, and that is the other extreme. So it turns basically almost 360 degrees, almost a full circle, but not quite. Those limits represent the extreme values of the potentiometer. Now, I also have a rotary encoder, also a knob. This guy, though, can turn and turn and turn and turn and turn and turn and turn. No limits. No limits. That's right. If you're looking for extremes, rotary encoders, no limits. So that is one difference between a potentiometer and a rotary encoder. A potentiometer has a limited turn radius. A rotary encoder has an unlimited turn radius. Another difference in the potentiometer versus a rotary encoder, a potentiometer is analog. So that means that it has 3 wires, generally. This guy goes, the red goes to power. The black wire goes to ground, and the white wire is called the wiper wire, and that is where the output voltage comes. And turning this knob adjusts that output voltage. Don't worry, we're going to do an object lesson. We're going to plug it into an oscilloscope and look at it. The rotary encoder, on the other hand, has a lot more a lot more wires coming off of it. If I zoom in a little bit and take a look at it, let's see. Can you find it? Might not be able to find it. That's okay. That's okay. I can switch over and look at it over here. Let's close some things and get me set up. Oh my. If I can figure out, there we go. Okay, so let's set up, let's at least give the episode a title. It's Rotary Encoders versus Potentiometers. Oh my! Lions and tigers and bears. Oh my! Rotary encoder, potentiometer. It felt like Rotary Encoder versus Potentiometer was a song. You know, like Rotary Encoder, Potentiometer, Constantinople, Istanbul. Anybody? Anybody? Yeah, it's a pretty nerdy song. But here is the Rotary Encoder up close, and you can see it's got a lot of pins off the edge of it. So it's got 1, 2, 3, 4, 5 pins. The Rotary Encoder has, let's see, it's got power and ground. You can see plus and ground. It has a switch. So that actually just means it's the output because you can press the Rotary Encoder. That's just because this is a fancy Rotary Encoder, so it has a push button switch. And then it has clock and DT for data turns. You could probably call them whatever you wanted, but it's got 2 pins that come out of it. And those 2 pins are used to determine what direction I'm turning. So if I'm turning it clockwise or if I'm turning it counterclockwise, the order that the pulses come out of these pins is going to determine which direction. So I have a website to help explain this because it's a little bit of a weird concept. This is the actual rotary encoder that I'm using. I'm using the KY040 rotary encoder. And you can see this is a better picture than the one that I just showed on my video, but I wanted to show that the actual rotary encoder I'm holding in my hand. It operates at 5 volts, which is good because the Raspberry Pi operates at 5 volts. It would be bad if it operated at not 5 volts. Rotary encoder basics. Here are the rotary encoder basics. It is going to output some pulses, and the order that those pulses are output is going to determine the direction that I am spinning the knob. So, with that said, let's hook up my rotary encoder and my potentiometer and figure out what the difference is. You'll notice my setup's a little bit more fancy here. I have put my Raspberry Pi on a piece of wood so it'll sit still. I've put my amplifier on a piece of wood so it'll sit still. I have now added this strange, mysterious board, which we're going to have to look at first. That board is a DC to DC adapter. In the previous demos, I have plugged the Raspberry Pi into usually the front of the oscilloscope through a USB port right there. But you know what? It's going to be hard to have the USB port from the scope in my garage at all times. So I thought it might behoove me to figure out how to use my fancy 24-volt power supply right here to power the whole amplifier, which is eventually the goal. And by eventually, I mean right now in 30 seconds. Let's turn on the power supply. You'll be able to see the voltage right here. If I put my camera, we should be able to see the voltage. Whoops. Goodness. Should be able to see the voltage hop up to 24 volts when I plug it in. Don't let the smoke out, Gabe. 24 volts. That's a good sign because it's a 24-volt power supply. Now, I have a 7-segment LED or a 7-segment display right here. This 7-segment display allegedly measures the voltage coming out here. So right now it should be 11.1 or 11.2 volts. I have 24 volts coming in on this side, and then through the magic of circuits, I should have 11 volts coming out on this side. Of course, we need to measure that to make sure that everything is working properly. I would hate to have this all plugged in and it not to work properly, and that would mean the end of my Raspberry Pi, which would be a bummer, I think. Okay, so we have this plugged in. In order to measure a power rail, does anybody remember what I should use on my oscilloscope to measure a power rail? I have all kinds of different accessories and adapters, but the one that we're going to use today to measure the power rail is the power rail probe. So this, if it can find it, let's see, there it is. The ZPR, can it find it? It cannot find it. Let's turn off a light here, see if that'll help. There we go. Not going to find it. I guess I'll have to tell you. There we go, ZPR40. It's the ZPR40. It is a power rail probe specifically designed to measure power rails. I'm going to plug that into the oscilloscope and into the output voltage right here. So let's plug it into the oscilloscope. I'll plug it into channel 1. And then I have 2 wires coming out, a plus and a minus. Let's connect it. So minus and plus. If I can get it. There we go. Minus and plus plugged in. Let's make a measurement. Let's make a measurement. Let's switch over to my oscilloscope. My handy dandy trusty oscilloscope. I'm going to make this slightly larger on my screen so that I can see it slightly better. Okay, here we go. First things first, when we're using our oscilloscope, we need to preset so that we're at a known state. Then I'm using the power rail probe, and that has a really cool tool in it called the probe meter. The probe meter will tell me exactly where this voltage is. It says that the voltage right now is at 11.12 volts. If I copy that to my offset, there's my voltage. So this is the voltage coming out of my power supply, which looks good because the LEDs say that it is 11.1 volts and the oscilloscope agrees, which is great news. Let's grab a little bit more time. Let's grab a millisecond, and let's turn this sample rate down. That's crazy. I don't need to sample a power supply at 10 gigasamples. Let's say a megasample. Okay, now I can see some noise on the power supply, which is a little bit of ripple. And in fact, we could, you know what? We can measure that ripple. So if I go to channel 1 and I make a peak-to-peak measurement on channel 1, I can see that my power supply has about 60 millivolts of ripple. And if I turn on statistics, I could see, instead of about, I can see that, yes, the power supply has 60 millivolts of ripple. I don't know if there's much that I can do about that, but I wonder, when I change the power supply to 5 volts instead of 11 volts, will the ripple remain the same? Will it still be 60 millivolts? So on my power supply is a little potentiometer right here, actually, that's going to adjust the output voltage. So as I turn this, it should change the voltage. If I go back over to my scope, you should be able to see the voltage swing off the screen, actually. So there we go. So I went up. Now I'm going to go back down, and I'm going to try to go down to 5 volts. And when the LEDs tell me I'm at 5 volts, I'll rescale the scope and find the signal. You can see my probe meter, 6.5. The LEDs match. So the LED, the 7-segment display on this guy, the measurement is pretty accurate. It's pretty awesome. I really appreciate it. It makes it a lot easier to set the voltage. Without an oscilloscope, you can just look at the 7-segment display. Okay, what does that say? 5 volts on the nose, 5.048 according to the scope. If I copy that to the offset, there's my voltage, and still getting about 60 millivolts of ripple. I wonder where that ripple is sitting, and I wonder if it's from the power supply or if it's from ambient noise in the techno layer. So I'm going to do a quick FFT. And yeah, there's my microphone. There's some Wi-Fi coming in. I got a lot of noise down here below my microphone, so it is quite a bit of noise. I don't know how that will affect. I don't know how that will affect the audio. I might have to do an audio test later on to determine if I need to do something to clean this noise up, because there is quite a bit of noise. There's a question, what makes a scope both handy and dandy? Probes, it measures voltage and current, handy and dandy. And it can, you know, if we minimize this, we could play video games on it, which I think is handy dandy. But we won't right now. Later. Okay, so this is my 5 volt signal coming out to my so I've set the power output to 5 volts. Now, I can use that 5 volts to power my Raspberry Pi if I use a few cables. On the Raspberry Pi, there are header pins, which I've talked about. One of the header pins is a 5 volt signal that I can use to power the whole Raspberry Pi. So let's start smart. Let's start smart, guys. Let's start with a ground connection so that everything's at the same potential. I hear it said that ground is pretend, but the word ground is real, and there is actual ground in the world. And if we connect two things to the same ground, really what we're saying is this is 0. So don't worry about anything else. This is 0. Now I need to hook 5 volts right here to this pin. And as soon as we plug this in, we should see some LEDs crank up, which is a good sign. Yes, we do. We have LEDs cranking up right there. There you go, LEDs flashing. I have this right here is my DAC. So this is my audio digital to analog converter. Then I have a whole bunch of wires going over powering my breadboard, and this is where I'm going to be doing the experiments for the potentiometer and the rotary encoder. I will start with the potentiometer. So I have power and ground coming into the signal, or system coming into the system. Yellow is power, green is ground in this particular circuit. So if I plug it in, now this center pin is the pin that I'm going to measure. So let's get my power rail probe out of the way and just hook up a regular probe, regular passive probe. Okay, so I need to hook the passive probe up, one side to ground. Let's get a ground side. Here's this long green wire will be my ground. So now that tells my scope where 0 is. And I'm going to hook the other side to the center conductor of my potentiometer. When we spin the potentiometer, we should see voltage change on the oscilloscope. So I'll spin it around a little bit. It's spinning good. That's excellent. Now if I go back over to my oscilloscope, turn the scope back on, here we are. Since I have made drastic changes to my oscilloscope, I'm going to preset it. And let's get a pretty big voltage scale. So 1 volt per division. That lets me swing 5 volts easily. If I move this down, let me move the offset down so that everything fits on the screen nicely. Let's put the offset at 3 volts. That'll let me go down 3 divisions, and now I can see everything. So here's 0 volts. Right now, it looks like the potentiometer is set a little above 2 volts. If I make a measurement here, I can actually determine exactly where it's sitting. 2.2 volts. Now, there is a question. If I limit the bandwidth, will it make the noise better? And I've done that in past episodes because I've drastically limited the bandwidth because all I really care about is noise that gets into my ear hole. The bandwidth of your ears is about 40 kilohertz. So if you limit the scope's bandwidth to match the bandwidth of your ears, the noise will go down quite a bit. I don't know. I don't know. I missed that question because it was way back in the FFT section. That's a good question. We're going to explore that. We're going to explore that power rail. Seriously? It's Baby Friday and I can't speak. We're going to explore that power rail a little bit more because I'm a little concerned that 60 millivolts is going to affect the noise that's getting into our ear holes. But that will be a future episode. Don't worry. We're going to come back to that. Right now, let's figure out if this potentiometer actually changes voltage. All right, there we go. So I have the potentiometer at one extreme, and you can see I'm down at 0 volts or thereabouts. Words are hard. The chat is encouraging me, saying that words are hard. Words are so hard. Why are words so hard? What if we could just communicate telepathically? If I could just look into your eyes, and we could just figure it all out. Like right now, in my mind, I'm telling you, I have the potentiometer at the other extreme, and it is 5 volts. That was all with my mind. Let's see if we can get it. Got it? Okay, so that's 5 volts. That's 0 volts. I can't spin forever. Now let's compare that to, that's how a potentiometer works. It adjusts the voltage on the center pin, on the wiper pin. Now I need to hook up my rotary encoder. My rotary encoders are a little different. It is going to have some pulse outputs. Instead of just a single output, it has 2 outputs. And we're going to see how that compares to the potentiometer output. So first things first, let's get this guy hooked up to power and ground. So ground first. There we go. We're all at the same potential. Now, let's turn this so you can see a little bit better. Now we got power. Okay, power and ground. Now I need to hook up some probes. So I'm going to hook up channel 1 to the pin labeled clock. And I have, luckily enough, a second channel over here. So channel 2 will be hooked up to the pin labeled DT. Data turn. Data awesome. Oh my gosh. Holy moly.
5 minutes remaining.
5 minutes left on this Baby Friday, so we better get cracking. We better get cracking. We better get back to it. DT, oh my goodness, look at this. I was so nervous when the 5 minutes went off. I hooked up my my signal conductor to ground. That's not going to be very helpful. That is going to really confuse us. One of the pulses would have been upside down and negative. Okay, so ground to ground. And the business end of the probe hooked up to DT. If there's any StarCraft 2 fans in the audience, Dark Templar. Dark Templar. Now, I have 2 signals. I have 2 signals hooked up. Clock and DT. I need to add the other channel. So let's turn on channel 2. There we go. Let's get these all scaled the same. So channel 1 is 1 volt. Channel 2, let's make it 1 volt. And let's make its offset 3 volts. So now we're all scaled the same. That'll be very helpful. I can even put these on 2 grids, which could be pretty helpful. There we go. Just make it pretty. It's a lot easier to understand. Now I want to set up a trigger. Right now the scope is triggering on channel 1, which is fine, but it's set to auto, which means the scope continues to trigger all the time. And if I spin it, it's really, I can see that stuff is happening, but it is not stopping for me to look at. I need to change this from auto to normal. Now you'll notice that the scope is no longer triggering unless it sees an actual trigger event. Here we go. There we go. I can tell that I'm not scaled out long enough to see the full pulse. This particular rotary encoder is rated at 20 pulses per revolution. So that means every 360-degree revolution, I should get 20 pulses. They're going to be pretty slow pulses. So let's go out to like 20 milliseconds. Really, really slow. Let's turn this record length to just whatever we want it to be. Let's make this 500 milliseconds. No. We'll make it even slower. One mega sample per second, which is 1 million samples every second, which is plenty to see a pulse. There we go. Now we got some pulses. Okay. You'll notice that I have what are called bounces. So if I go over here and zoom in on this particular section, the signal goes up and down and up and down and up and down and up and down, and finally it settles. That is called bouncing. That's what happens to every analog switch or encoder or any kind of analog system will have a bounce. Some digital circuits have a debounce circuit built into it. So as soon as the signal goes low, it will latch low and stay low for a certain amount of time. So maybe you'd set up a latch for 100 milliseconds or something. In the software for Moode audio, it actually has some debounce algorithms built in to avoid catching all these bounces, because this would be bad if the software thought that the signal was actually bouncing up and down that much. It needs to ignore those bounces. And we can do a little bit of that ignoring if we go into my HD mode, and let's change the bandwidth way down. Let's change it down to a couple of, 10 kilohertz is as low as we can go. Let's see if that cleans up any of the bounces. A little bit. You can see right there, that is a super clean edge. I zoom in, no bounce. So that is one way you can adjust the bandwidth just so it doesn't see the bounces. They're not going to be affecting the software, because the software is going to debounce itself. Okay, so that was, let's go back to figure out what's happening. If I turn the rotary encoder clockwise, so this is clockwise, I'll click it over one click clockwise. So click, there we go. We can see that channel 2 leads channel 1. That is how the direction is defined. If I click counterclockwise one click, channel 2 should lag channel 1. And you can see, oh, that was a weird one. There we go. It's lagging by so far, it doesn't even see it. So I might need to grab even more time. Let's grab even more time. Let's grab a ton of time. 400 milliseconds. Hello, there we go. There's the falling edge, lagging, rising edge, lagging. Other direction, leading. And that's how it determines the direction. So it can tell clockwise from counterclockwise. And that's what an encoder is all about. It's trying to determine the direction, and then from there, your software takes over. And it counts how many pulses that it saw, and then in this case it's going to adjust the volume, hopefully, if we hook it all up right, either higher or lower, depending on if it was clockwise or counterclockwise. So that's an encoder versus a potentiometer. Potentiometers, only analog voltage. This would be, and that's actually what we used to set the DC to DC converter. There was a potentiometer on there that adjusted the analog voltage. But the software wants an encoder, and that is where we needed to figure out how an encoder worked, what it was looking for. It looks like it's got 2 pins, and the order that the edges come out determine what direction the encoder is spinning. Hopefully that explained potentiometers versus rotary encoders. They're both used to control volume a lot. One is really geared towards a fully digital system, that is the encoder. The potentiometer is geared towards an analog system, so you would need some way to read that voltage out, so you'd need an analog to digital converter, which would add another layer of complexity to your design, which is why encoders are so cool, because it's just ones and zeros and it's just edges. We're just looking for the order of edges. We don't care about voltages, order of edges. Digital signals love edges. They do not love analog voltages that much. They want edges. As usual, I don't know all the nerds in the world, and I would love to meet them. Please share this with a nerd in your life. I'm going to hang out in the chat. Let's make sure that I didn't miss anything. In the chat, there was a question. Where did I get the cool header adapter for my passive probe? Man, guys, you got to get the right tool for the job. I noticed that there's an accessory kit that I could get for my passive probes. And in the accessory kit were those really handy header adapters. So I ordered a couple of accessory kits, added it to my passive probes, and now my passive probes can hook up to just about anything. So much better than that witch's cap clip, which is really hard to hook on to just about anything. And the header adapters make it a lot easier. So that's a pro tip for a Baby Friday. Thank you so much for joining. I'm going to hang out in the chat a little bit longer, and I will see you guys next week. Have a wonderful weekend. Bye.